So now let's have a look at some of the results. And the first set of results is for the transformer architecture and the ASR task. And we see these 6 panels here. The first row corresponds to the diagnostic classifier condition. The second row corresponds to the representational similarity analysis. And then we have the 3 columns. The first column is the local scope. The second and third column are the global scope with mean and attention pooling respectively. So what do we see in general? We see a strong effect of learning in the sense that the red and cyan lines are clearly separated. So there is a large difference between the trained and untrained model in terms of what they encode in terms of phonological representations. One thing that also stands out a little bit is that for the condition with local RSA, we see only weak correlations, whether with trained or non-trained model. The correlations are quite small. Now moving on to the RNN architecture for the ASR task. We see that the effect of learning is stronger with global scope. So you will see that the first column, the separation between the red and cyan lines are much smaller than in columns 2 and 3. And we also see substantial encoding of phonemes shown for random target model with local diagnostic classifier. So I am referring here to the first row, first column. You will see here that even though the trained and random or untrained models show some separation, it is nevertheless the case that the randomly initialized untrained model also encodes, or at least according to the diagnostic local classifier, encodes phonology to a substantial degree. And the similar results hold also for the RNN architecture with a visually grounded speech task. What we do see, the one difference we do see is a weaker encoding of phonemes in the top layer. So if you compare it to the previous slide, you see that in this slide, at the last layer, we still typically in most cases get an increase in the score. And here, in most cases, we don't get an increase and we might even get a decrease. So that is not unexpected in the sense that there are 2 different tasks, ASR and VGS, and VGS is a more high-level task in the sense that it needs to encode some at the top layers, it needs to encode some degree of visual semantics and not focus so much on the phonological form. I wanted now to zoom in into the difference between the transformer versus the RNN architecture for the local diagnostic classifier, and specifically looking at the random untrained target model. So you can see that the cyan line here is flat for the transformer, but it increases initially for the RNN architecture. So this may be due possibly to the different connectivity in these 2 architectures. The connectivity is local in an RNN architecture. So that means that if we go higher, if we go up in the layers, the higher layers have access to more time steps of the input. Even with random weights, they can still combine them in some useful way. Useful in the sense that we can then decode phonemes from those layers. In the transformer, the connectivity is global, meaning that already in the first layer after the input, all the time steps are accessible. So with random weights, higher layers do not add much on top of that. So that's one possible reason for this pattern that we see here. Um, Another thing I wanted to discuss is that we do not see such a difference in the global scope. And so, why is that? Well, we speculate that pooling across time for random RNNs cancels out information in the sense that maybe information is encoded at each time steps in some way which is decodable. But then once we pool for an RNN with random weights, this kind of cancels out. This information is lost. However, once we train an RNN, then these activations become robust to pooling because the model has a self attention pooling operation as part of its architecture. So via the process of learning, these local representations become actually such that after pooling them, they still contain useful information because that's what the model needs to learn in order to perform the task that it's trained on. So this is speculation in the sense that we don't have like hard evidence for this. We do have some suggestive patterns, which I will not go into because it will take too much time. But I'm just mentioning it. So in terms of recommendations that we can derive from these experiments, for these sets of experiments. So the first one is that analyses on randomly initialized, untrained target models should be included typically as a baseline because that allows us to disentangle what part of the representations that we are analyzing are due to simply the setup of their architecture itself and what they carry over from the inputs into the different layers, and what is due to training the model and what it's learning from the process of training. Another recommendation I would like to give is that we would typically want to confirm findings with multiple analytical approaches. Analytical approaches they have different characteristics. They work under different conditions. We don't fully understand always like their weaknesses and strengths. So I think it's safe to always use several of them. See in what cases they agree, in what cases they disagree. This gives us a much more fine-grained and accurate picture of what is happening than just trusting a single metric and going with it. And finally, although the typical approach is to use local diagnostic classifiers, we would want to also advocate to the use of global methods applied to pooled representations. I think this gives us another complementary view on the nature of these representations that we're trying to analyze. So one thing we have also seen in the course of this work is that there are some very hard limitations which are very hard to go around. So we tried um, to have a properly controlled set of experiments, but full control of all the factors of variation in target models is not always possible. So if you change the model from the task of the model from ASR to VGS, you may need to change not only the task itself, but also some parts of the architecture may need to be changed in order to make the task possible, and that makes the comparison less direct. And also in the choice of analytical methods, some factors can be entangled with other choices. So to give you an example, unlike a global diagnostic classifier, global RSA captures a sequential order of phonemes, whereas a global diagnostic classifier does not capture the order of phonemes, but only the presence of phonemes as such via this binary vector of phoneme indicators. So full control is not always possible, but we should strive towards it. And finally, I wanted also to mention a couple of things that both our group and other groups are working on in the space of visually grounded models of spoken language. And one very interesting development is our discrete representations. So discrete representations are uh, in a way thought of as incompatible with typical neural representations, which are distributed. But there have been some efforts to marry these two ways of representing information, and we now have some ways of including uh, discrete symbolic representations as part of neural architectures, including visually grounded models of spoken language. And so these discrete symbolic representations are very interesting in the sense that they are much closer to typical linguistic structures that we would use in linguistic theory. And so this is for us one focus of interest, what we are currently trying to look into. Uh, Another thing that is also very interesting and which I barely mentioned in the lecture so far is grounding spoken language in video rather than in static images. So with static images, uh, you get the static scene, you get the some particular objects which are in the scene, but it can be difficult to get what the relation between these objects are, what are the actions which are happening, what is the overall situation. And so video may give you this additional source of information which may help with the grounding of some parts of the language, such as like verbs, for example. But it comes with its own challenges also, like with a caption and a static image. We are guaranteed that they're somehow connected with video and language. There could be some temporal discrepancies between when a particular object occurs or a particular action takes place in the video and when it's being spoken to it. They do not necessarily have to be very closely temporally. So that's a challenge. There are some other challenges. We'll see what they are once we get some results with this approach. So that concludes the lecture. Thank you. I hope you enjoyed it.